We have looked at, thus far in this unit, Newton's first law. Newton's first law, as we just talked about a minute ago, says an object at rest stays at rest, and an object in motion stays in motion in a straight line at a constant speed until acted upon by an unbalanced force. In other words, the net force acting on an object at rest is zero. We may have forces acting, but the net force is zero. The net force acting on an object that's moving at a constant speed, again, we may have forces acting, but the net force acting on that object is, again, zero. That's Newton's first law. Yesterday we talked about Newton's second law. Newton's second law relates to the acceleration of an object. The acceleration of an object is dependent upon two things. What are those two things? What's one of them? What's the first one that the acceleration of an object is dependent upon? What's one thing that affects the rate of acceleration here? Mason, what's the answer to that? What's one thing that affects the rate of acceleration? Force. Not just a force, but the net force. So when we were looking at that thing that we did a minute ago here with Nick is pushing the desk one way, friction is acting the other way, I'm pushing the other way as well. It's not Nick's force that's important in determining what the acceleration of that desk was, it's the total, the net force that's important, right? My force combined with Nick's force, combined with the force of friction, that's what determines what the acceleration is. Okay, now sometimes there is only one force, but we have to consider the total force, whether it's made up of 1 or 14 forces. It's dependent upon the net force. And we know that the bigger the net force, the bigger the rate of acceleration. So it's going to go on the top, right? F is going to go on the top because they're linearly related to each other. Bigger F, bigger A. What's the other thing now that affects the acceleration in the opposite way to force? What's the other thing? Nick, you have an answer for this one, right? What's the other thing that affects the acceleration? The mass. And the mass affects it inversely. So in other words, the bigger the mass, the smaller the acceleration. You push on a little car, let's say a little Honda Civic, with a certain force. You push on that Honda Civic with a bigger force. When you push on it with a bigger force, the acceleration will be bigger. You push on a Honda Civic with a small force. You push on a semi-truck with a small force. Same force, but the Honda Civic will accelerate at a greater rate because its mass is smaller. So bigger force, bigger acceleration, bigger mass, smaller acceleration, right? That's why m is on the bottom there. In other words, we say in words, the acceleration is directly related to the net force, and it's inversely related to the mass. Or we can just put that into an equation, a is equal to F over m, which appears on your data sheet as F is equal to m times A. Got it? Go ahead, Rucker. Oh, don't even get me started on that triangle. Don't even get me started on that triangle. The little 3-variable equations can be rearranged with that little triangle that sometimes your junior high teaches you, much to the chagrin of high school teachers. Even some teachers in England, I hear, teach that little triangle. They drive me and every other high school science teacher crazy. Because all of a sudden, when you're dealing with an equation that's not a 3-variable equation, that triangle is useless. And try rearranging d is equal to vit plus 1 half et squared, rearrange it to solve for t using that little triangle. That little triangle, right? It just doesn't work. Okay? F is equal to m times 8, sure it would. But look, if we have to know algebra to do d is equal to vit plus 1 half et squared, well, then the algebra for this is easy, right? So let's not go with that little triangle. Even though your junior high teacher may have taught you that, let's not go with it. Because it doesn't really work for us for most equations that we do in Physics 20, or in Physics 30 for that matter. All right. We also yesterday talked about 3 types of forces, 3 specific types of forces. The first one we talked about was weight. Weight versus mass. Mass is the amount of matter that you possess. I possess 70 kilograms of matter. You might possess 80 kilograms of matter. You might possess 60 or 50 kilograms of matter. But the amount of matter that you possess will be the same anywhere in the universe. If you get on a spaceship tonight and go to the moon, your mass will not be less on the moon than it is here. If you go to Jupiter, okay, your mass will not be greater on Jupiter than it is here. If you go to the furthest depths of space, as far away from anything as you can possibly be, your mass will still be exactly what it is right here. Mass is the amount of matter that you possess, and that doesn't change. Weight, on the other hand, does change. And it changes because weight is defined as what? Yep. The force of gravity acting on an object, right. The force of gravity acting on me is about 685 newtons. Okay? That changes because of the way that I find the force of gravity. Okay? The way that I find the weight. And the force of gravity is equal to m times the acceleration of gravity. Sometimes we see that written, by the way, as F is equal to m times g. Same thing. The acceleration due to gravity is 9.81 meters per second squared here. But on the moon, the acceleration due to gravity is only about 1.6 meters per second squared. On Mount Everest, the acceleration due to gravity is somewhere around 9.6 meters per second squared. It changes. So if g changes, then the value of F will also change. Quickest way to lose weight? Go to the moon. It only takes you a few days to get there. Okay, when you get to the moon, you're going to weigh only 1/6 of what you weigh here. You weigh 600 newtons here, you're only going to weigh 100 newtons there. Your mass doesn't change, your shape doesn't change, but your weight technically does. You lose about 5/6 of your weight. The only problem is when you come back, what's going to happen? It's the quickest way to lose weight to go to the moon, but it's also about the quickest way to gain weight when you come back. Because, of course, when you get back, you're going to be the same as you are right now. Weight is the force of gravity. Mass is the amount of matter that you possess. Weight changes depending on your location. Mass doesn't. Second force we talked about was the normal force. The normal force is the force of the ground, or whatever, pushing up. And remember I said that in quotation marks yesterday, pushing up? Because it's really pushing at 90 degrees. It's really pushing at 90 degrees on you. Okay. If you're on the ground, like this, okay, then the normal force pushes up on you, straight up. But if you're on a hill like this, that's a pretty steep hill actually to be standing on, but let's pretend you are. Okay, on that hill, then the normal force pushes up like this. Again, at 90 degrees to the ground. Does that make sense? Is there ever a situation where the normal force could actually be not up at all, but rather sideways or down? Could you have a normal force, the force of the ground, pushing on you sideways or pushing on you downwards? Well, yeah, then it's not really a hill, right? Then it would be, yeah, it would be a cliff, actually. Yeah. If you're ever traveling down the road, you know, you see those signs on the highway when you're going down big hills. Okay, it'll say, you know, like an 8% decline or whatever, right? 7%, 8%, whatever. You know, you get into a steep hill, and semi-trucks especially, you have to gear down, and you have to be ready for this big hill, right? If you ever see that it's 100%, then you should stop, because it means you're going to go off the edge of a cliff. Okay. Well, okay. So you're not. I guess you're not technically going off the edge of a cliff, but you're pretty close to going off the edge of a cliff. You never see 100%. You're never going to see 100% on the highway. If you do, then try to avoid it. Okay. So we got 100% right here. What about this one though? What about? Well, can you ever be standing here? You guys ever seen those Batman cartoon videos? They're from like the 80s or 70s, but sometimes they're on like YouTube or whatever. Batman did that all the time. Batman, the cartoon videos at least, did that all the time. You could be scaling something. You could have a rope right here. Okay. Maybe you got a pulley up here. Hey, I was in Las Vegas this summer, and all of a sudden, I open up the blind in my hotel room on the 11th floor. There's a guy standing there. Literally, there's a guy standing there outside my window. And I thought, well, it's a good thing. Like, it's a good thing I didn't come out of the shower with, like, you know, a towel on or worse or whatever. And there's a guy standing there. And I think you have privacy when you open the your blind on the 11th floor of a hotel, right? But there's literally a guy standing there cleaning my window as I open up the blind. He wasn't doing this though. He wasn't there with his feet against the window. But if you're scaling something like a cliff or a building, then you would, right? You would have your feet there. The normal force in that case would be pushing out on you because it pushes at 90 degrees, right? What about pushing down on you? Could the normal force ever push down? If you had suction cups on your feet, no, actually. No, that's a good guess. But if you had suction cups acting on your feet, then the floor above you or the ceiling above you wouldn't actually be pushing you down. It would be pulling you up. Well, yes, okay, whatever you want to call it. It would be technically the vacuum pulling you up, right? But the ceiling still isn't pushing down on you, right? Why would it be? Gravity's pulling down on you. Okay, if gravity is pulling down on you, and the suction cup is keeping you up, there's no reason for the ceiling to be pushing down on you. Okay, if you're hanging from the ceiling, think about that. If you're hanging from the ceiling, how can the ceiling push down on you? Okay, so there's somebody that's gone over the ledge of the ledge of a cliff, whatever, and you're holding on to that person. You're holding them up with your hands, right, to keep them from falling over the cliff. You're not pushing down on them. You're pulling up on them, right?
Yeah, but
okay.
Yes, but if you were on the ceiling,
yeah,
then the force from the vacuum would have to be greater than gravity, otherwise it would be falling.
It would have to be equal to or greater than gravity. Wouldn't necessarily have to be bigger. Wouldn't have to be bigger.
But if it was bigger, wouldn't that be a normal force?
No. Yes, actually, yes. Yeah, if it was bigger, then yes, it would be possible. Yes, yeah. So if you twist it around enough, then yes, that's possible in that situation. Yes. That's not the one that I was thinking of. Do a handstand. Oh, the ground is still pushing up on you, right? Okay. The one that I was thinking of is one that you're going to encounter, that all of you hopefully will encounter end of November, beginning of December when we take our field trip to Edmonton. Okay. That is when you're riding on a roller coaster and you're upside down right here. Gravity is pulling down on you, but what else is pushing down on you? The track. The track provides a normal force. The normal force would be down in that case, unless you're going at the bare minimum speed to go around there, which is not really what you want to do. There's a certain speed below which you'll actually fall out of the loop, above which you're fine. There's a minimum speed that you have to be going to go around that. There's safety mechanisms if that doesn't quite work out, but you don't need to worry about it. But theoretically, above that minimum speed, you're fine. Below that minimum speed, you'll fall out. If you're going at the minimum speed, then the track doesn't actually have to push down on you. But above that minimum speed, gravity isn't strong enough to pull you down. The track has to help gravity push you down. Okay? That make sense? So we normally think of the normal force as being straight up, and it usually is. But every once in a while we see something like this. Every once in a while we see something like this, although something like this is pretty rare. And then occasionally we see something like this, where the normal force is pushing down. By the way, didn't mention this yesterday. The normal force is how heavy you feel. Okay, your weight is how heavy you are. The normal force is how heavy you feel. Okay, we'll call the weight your actual weight. We could call the normal force your apparent weight. I weigh about 700 newtons right now. How heavy do I feel? 700 newtons. Why? Because gravity is pulling down on me at 700? No, that's not why I feel like I weigh 700 newtons. I feel like I weigh 700 newtons because the floor is pushing back up at the same as gravity is pulling me down. If I'm in an elevator, you ever experienced this? I'm sure you have. If you're ever in an elevator like the CN Tower or something, an elevator that accelerates at an incredibly fast rate. Okay? You get this high rate of acceleration. How many people have been in the CN Tower? Just a few of you? Wow. You accelerate upwards like, I don't know how many stories it is. It's massive. It used to be up until like last year the world's highest freestanding structure. You accelerate incredibly quickly up to the top of the CN Tower. You feel like what as you're accelerating upwards? You feel heavy, don't you? You feel like you're being pushed down against that floor, right? Well, that's because the normal force is bigger than gravity. My weight in the CN Tower elevator is still 700 newtons, but my normal force might be 900. So how heavy do I feel? 900. How heavy am I? Am I actually? 700. It goes the other way around too. When you're at the top and you're going down, you accelerate downward. The normal force is less than gravity because you're accelerating down. So what happens? You feel lighter. Your stomach kind of goes up into your throat, right? When you're accelerating downward because you feel lighter. You're not, you feel lighter. Make sense? I think we talked about this one day, just as a little aside thing here. Astronauts orbiting around the Earth. Did we talk about that one day? The astronauts orbit around the Earth in a shuttle or in a space station. They're weightless, right? No, they're not weightless at all. They have almost as much weight as they do here. If I weigh 700 newtons here, I may weigh 600 newtons as I orbit around in the space station. So why do I appear weightless? Why do I feel weightless? Because this space station it's going out, but as it goes out, it also constantly falls. It's free falling. As it free falls, the normal force pushing up on your body is 0. Why do I feel weightless? Because there's no normal force. Why am I not weightless? Because there's still gravity. If gravity is how heavy I am, normal force is how heavy I feel. That third force that we talked about yesterday was friction. Now we're going to get into a little bit more detail on friction here today. Okay, we said yesterday that there were two kinds of friction. The first one was static friction, and that was the one that kept an object from beginning to move. Okay, Lane's desk again. Lane's desk is at rest. The net force acting on that desk right now is 0. I give it a little push of 5 newtons. Still doesn't move. That must mean there's a force of static friction of 5 newtons pushing back that keeps it from beginning to move. The force of friction that prevents an object from beginning to move. Now, what's wacky about this force of static friction is that it changes depending upon how hard I push. What's the force of static friction on Lane's desk right now as it just sits there? 0, because I'm not pushing on it. What's the force of static friction when I push on it with 5 newtons? 5 newtons. What's the force of static friction when I push on his desk with 10 newtons? 10 newtons. Static friction responds to how hard I push. It's as big as it needs to be in order to keep the object at rest. But it does have a maximum value. And when you apply a force above that maximum value, then it can't hold it anymore, and it begins to move. So let's say the maximum force of static friction on Lane's desk is 12 newtons. Okay? I push on it with 5. What happens? Does it move? No. Static friction is 5 and balances it. Push on it with 10. What happens? Static friction is 10. Balances my applied force. Push on it with 11. What happens? Doesn't move. Push on it with 13. What happens? It moves. Static friction was what it had to be until I exceeded it. And then the object began to move. Okay, until I reach a maximum value, then it begins to move. Kinetic friction, on the other hand, sometimes we call it dynamic friction, is a force of friction that acts against an already moving object. So As I pushed on Lane's desk with 10 newtons, with 11 newtons, static friction became 10 newtons. It became 11 newtons. When I pushed on it with 13 newtons, the desk moved. Now the static friction was 0 at that point because it was moving. Now it's kinetic friction that kicks in. And the force of kinetic friction would be lower than the maximum force of static friction. So listen very carefully to this example again. Okay? Listen very carefully to the details and to the numbers involved in this example again. Lane's desk right now has a net force of 0 newtons acting on it. It's at rest. The force of static friction, the force of kinetic friction is 0 because nothing's happening to it. The max force of static friction on Lane's desk, we'll call it FSF max, we said was 12 newtons, right? Okay, so I'm going to push on his desk with a force of 5 newtons. What's the force of friction acting on his desk? I pushed on it with 5. What's the force of friction? 5. What kind of friction is it? So it's 5 newtons, and it's static friction. Okay, I'm going to push on it now with a force of 10. What's the force of friction? 10, somebody said. And what kind is it? Static friction. I'm going to push on it with a force of 11.9. It's not moving. What's the force of friction acting on it? 11.9. It's however hard I'm pushing, right? What kind is it? Static friction. Let's push on it with 12.1. With 12.1 newtons now. It moves. What kind of friction do I have now? It's not static anymore. It's kinetic friction. What's its value? It would be more like 8 newtons, 9 newtons. Okay. When it starts moving, kinetic friction kicks in, and kinetic friction is not necessarily lower than static, but it's lower than the maximum value of static. The max value was 12. Okay. Force of kinetic friction would be something like 8 or 9. Does that make sense? Talked about this yesterday, right? Why is it easier to keep an object moving than it is to get an object starting to move, right? I tug and I tug and I tug on this desk, can't get it moving. But once I've got it going, it's easy, or at least it's easier to keep it going once I've already got it moving. Travis? Yes, that's a good question. Kinetic friction is a constant value. So let's say I pushed on it with a force of 500 newtons. What would be the force of friction on it? It would accelerate at a pretty big rate, right? What would be the force of friction on it? Sorry? It'd be 8, right? Or whatever the force of kinetic friction was before. Okay. Once it's moving, kinetic friction isn't going to change. It's always going to be 8 newtons or whatever it is. Okay? Once it's moving, regardless of how much force I apply, no matter how fast it's moving. Got it? All right, let's give you a couple equations. The first one is actually not an equation. It's an inequality. The force of static friction. Notice I put absolute value signs around that. That means that we're not going to get any kind of direction from these equations. It's only going to tell us how big the force is. It's a vector. There is a direction, but we're not going to get the direction from the equation like we do with most of our equations. The force of static friction is less than or equal to something that we call mu. That's like a handwritten U almost. It's a Greek letter that we call mu. Tell you what that means in a second. Times the normal force. And the normal force is usually the same as the force of gravity. Okay, we'll provide you with some situations over the coming days when it's not the same value, but for now, it'll be the same value as gravity for us. What does mu stand for? It's what we call the coefficient of static friction. It basically measures for us how much these two things stick together, how much the legs of Lane's desk stick to the floor. The higher the value of the coefficient of friction, the more they stick together. So for instance, rubber on asphalt would have a higher coefficient of friction than would rubber on ice. That's why we want to be on asphalt in our cars as opposed to on ice, because it stops better. The coefficient of friction is bigger, the force of friction is bigger. That's why the coefficient of friction of, what's that stuff that's in your frying pan, the nonstick, what's it called? Sorry? No, not Pam. Teflon. Yeah, that's what I was thinking, Teflon. That's why Teflon has a lower coefficient of friction than does steel. Okay, because things stick less to Teflon than they do to steel. And Pam, talking about putting Pam in there to cook, I mean, it accomplishes the same thing, right? It reduces the coefficient of friction. Now, this is an inequality, so we can't actually solve for a value of force of static friction there. We can only get a max or a value that it has to be less than or equal to. What we're actually going to do in practice is modify that a little bit. We're going to say the maximum force of static friction is equal to mu times the normal force. In other words, this is the maximum force. The force of static friction will either be less than or equal to the maximum force. In that example that we gave with Lane's desk, what was the maximum force of static friction? It was, no, the maximum force of static friction was 12. Good. The max force was 12. So the force of static friction that we had was either less than or equal to the max value. Let's go back here again. The force of static friction was 5. Is that less than or equal to 12? Yes. 10. Is that less than or equal to 12? Yes. 11.9. Is that less than or equal to 12? Yes. So static friction can change, but it's always less than or equal to this number right here, the maximum value, which in that case of Lane's desk was 12. Even though this is the one that appears on your data sheet, this is the form of it that you're going to end up using. FSF max is equal to mu times the normal force. Now the other equation that we have here is FKF, the force of kinetic friction. And we're not going to say any kind of maximum here because it's always the same value between two surfaces. It's equal to mu times the normal force as well. But this mu is the coefficient of kinetic friction, and this mu was the coefficient of static friction. It's not less than or equal to a certain number. In that last example we gave, it was 8 newtons. If it's 8 newtons, it's always going to be 8 newtons. It doesn't change like static friction does. This we call, by the way, the coefficient of kinetic friction, or the coefficient of dynamic friction. Sometimes we actually see this called not just kinetic friction or dynamic friction, but sliding friction. If something is sliding, it's kinetic friction. You see a table up on the board here right now. We'll have a quiz on that tomorrow. Make sure you know all those numbers for tomorrow, please. No, we won't. You don't have to memorize any of those numbers, of course. I don't have them memorized. Why would I expect you to memorize them? That's something that we can look up easily, right? This is just a table for reference. It gives us different coefficients of static friction and kinetic friction. You can see that the coefficient of kinetic friction of steel on steel, of static friction of steel on steel is 0.41. So when steel pushes against steel, They stick together at 0.41. That's what keeps them from moving. The coefficient of kinetic friction is 0.38. Let's go back to rubber on wet dry asphalt. That's a pretty high value of static friction, right? 1.2. Kinetic friction, it's 0.8. So why do we have why do we have rubber in our tires? Part of it is for balance, right? But part of it is for, yeah, we have good grip, right? We have a fairly high coefficient of friction there, which gives us a big force of friction, which gives us good grip. It makes it easier to stop. What about a curling stone on ice? Well, those are pretty low, right? Why do we have a low coefficient of friction for a curling stone on ice? Because we want the curling stone to slide on the ice, not to stop as soon as you throw it. Can you imagine taking a curling stone made out of rubber and sliding it down the pavement and expecting to play a game of curling? Because of the coefficient of friction between rubber and asphalt, it just wouldn't work, right? What do you notice about all of these, though? What kind of pattern do you notice about all of these coefficients of friction, whether we're talking about rubber tire on asphalt or a curling stone on ice? Travis? Kinetic friction is less than the force of static friction. Remember what we said a minute ago? The force of kinetic friction is normally lower than, not than static friction, but the maximum possible force of static friction. Lane's desk, static friction was 5 the first time. Kinetic friction was 8. But the maximum force of static friction on Lane's desk was 12. And kinetic friction was still 8. So it was lower than the max value. Yep. When would it be higher? I can't think of a situation where it would be higher. No, it still wouldn't be higher because, no, that's a good question, though. That's a real good question, actually. Travis just said, basically, if you're pushing up a hill, doesn't that change the whole nature of static friction, kinetic friction, because of the angle? The normal force is different now, right? The thing is, though, if you look at that max force of static friction, it's mu s times Fn. If you look at the force of kinetic friction, it's mu k times Fn. So even though that normal force does change, it decreases quite dramatically there. It decreases for them both. So if it happens for one, it happens for both of them. Basically, if this value is bigger than this value, then the max force of static friction will always be bigger than the force of kinetic friction. Okay? Here's a question. And we're going to need those numbers to answer this question, but we just don't need to memorize those numbers. .17 on page 185. A sled with waxed hickory runners rests on a horizontal, dry, snowy surface. Calculate the mass of the sled if the maximum force that can be applied to the sled before it starts moving is 46 newtons forward. What do we have given to us here in this question? Forget about the table for a second. What's given to us in this question right in front of you right now? Yep. The maximum force of static friction. Okay, I could rephrase this question to go back to the example of Lane's desk here. Could rephrase it to say, calculate the mass of Lane's desk if the maximum force that I could apply to the desk before it begins to move is 12 newtons, right? Push on with 11.9, nothing happens. 12.1, something happens. So the maximum force of static friction, we're going to call it SF max is equal to 46 newtons. Now, since we're dealing with static friction, we want the coefficient of static friction between waxed hickory runners and dry, snowy surface. Waxed hickory runners on dry snow. Static friction is 0.06. Who's a skier here, by the way? I haven't skied very much in my life. Maybe a half dozen, maybe six, 8 times in my life. I like it. I like skiing. The last time I went skiing was I think it was in April last year at Lake Louise, and it ended up being a day where it was like +3. And I found that it was much, much more difficult to ski on a day that I was excited because I thought, oh, this is going to be nice. I don't even have to wear a hat. Right? It's +3 or a hat or mitts. I can take my mittens off, whatever, or my gloves off. But it was brutal. Like snowing when it's skiing when it's +3 is brutal. Why? What happens to the snow when it's +3? Sorry? It gets wet, right? It gets sticky. Look at the coefficient of friction between skis on dry snow versus skis on wet snow. It's a lot harder skiing down the hill in wet snow than it is in dry snow because the coefficient of friction is more than 3 times greater. So it's warm and it's nice that way, but it's not very nice skiing. Okay, we want to find the mass here. Any ideas? Well, we know the maximum force of static friction is equal to mu times the normal force. Now, this isn't the actual value that we have at any given time. This is the maximum possible value. We have that value. We have mu. We don't have Fn. Let's solve for Fn here. It equals FSF max over mu. So it equals 46 newtons divided by 0.06. What does that give me, somebody? 46 divided by 0.06. 766.7 newtons. Thank you, Hayden. That's my normal force. But we said, for us at least right now, the normal force will be the same as the force of gravity. So we can set that equal to m times g, where g is 9.81 meters per second squared. So we've got the normal force, which for us right now is the same as gravity, force of gravity. Set that equal to the force of gravity. Solve for the mass here. 766.7 newtons divided by 9.81. What do we get there? Sorry, what do we get there? 78.15. We're going to round that to 78 kilograms. Now notice I dropped the sign of the 9.81 there. Everything is magnitude when we're talking about friction. Okay, forget about direction. Okay, we'll deal with direction in some other way. Everything is magnitude here, how big the force is. Is that okay? Now, that would have changed a little bit if you weren't on a flat surface, because then gravity wouldn't have been the same as the normal force. But again, for now, we're going to deal with just situations where gravity is the same as normal force. So you can consider them to be the same thing if you want, for now. Okay. Finish copying that out if you haven't copied it already, and then we'll give you your 2 practice problems to work on. Questions 1 and 2 on page 185. Let's see what we can do with those, please.